Okay, we are live. We have Rohit and we have Tara.
Hi.
They're gonna shadow today. Let's see. Rohit, do you remember what we were working on? Been a little while now, so I don't blame you if you can't remember.
It's been a little while. I think the last I remember was we had a simple file system up and we were trying to integrate with the web. Like we were trying to make the web.
Ah, yes. There was a DOM device. Well, I've got
Yeah.
an update that I can show, a couple of updates. And yeah, let's get into that. So for people that are watching, if anybody's new, a year ago, put together an experimental abstract WebAssembly. Not a traditional operating system, but kind of almost like I want to say like a virtual operating system, maybe. And there was, we made a bunch of demos and stuff. You can check out this video at wanix.sh. But now we're rewriting it from scratch because one of the core ideas that I wanted to build into it was Plan 9 style file systems. We didn't actually do in the original version. So let's see. Since the beginning of the month, we've been basically building up some code, some abstractions, and really focusing on the Plan 9 file system stuff. And then from there, we can do a lot of cool stuff. Let's see. In the last, I do remember last time we did, since we started doing the web stuff, I shared this prototype, and I don't think I shared this, but this is kind of the script for the paper prototype demo that I did, which was done before we started the stream or anything. And our goal, kind of the initial goal, is to get to the point where this is all pretty real. And just as a kind of a recap here, what we will have in the browsers, we create a Wanix object, which pretty much just has file system operations on it. And we can use that to read this virtual file system that Wanix provides. And there's a couple of sort of root directories that represent different devices. So Wanix has file systems as a sort of first-class citizen, and kind of trying out experimentally calling them devices. So there's a file system device that lets us manage these file systems. And these are file systems that aren't necessarily about, one of the ideas in Plan 9 is that you're exposing a lot of what the kernel and the operating system would normally provide via syscalls over the file system, which then lets you use shell tools and stuff to interact with the system and let you kind of compose and extend the system all through the file system, which mostly means the file system API. So we're sort of reducing the API surface area. So it's like we're getting a lot out of this very simple API. So in this prototype, the idea was, okay, we'll look at this file system. You can see there's a control file and a directory of called new, and in new there's a bunch of types of file systems that could be created. What was then called, I was calling hostfs. I could call pickerfs now. Uses the browser API for accessing directories on your actual file system, since normally the browser is a sandbox environment. They can't access the rest of your system. You can give it access to certain directories. So this would expose that as a sort of a new resource that's now under file system 1. And if we look under file system 1, you'd have a control file, name and type. If we looked at name, it would be the directory that I had opened. And it looks like these control files, it's a common pattern for Plan 9. We can just write to it to basically perform a command. So it's sort of an alternative to, sort of gives you access in a way to low-level stuff, but what you could normally do over a shell. In this case, I'm calling these functions directly, and so this isn't as convenient, but the idea is that we bootstrap an environment that would eventually give us a shell. So once we have this pickerfs from, basically represents a directory on my hard drive somewhere, we can then bind it to /data, and then there is a root directory called data that would have access to it, and we could interact with files on my host computer. So that was kind of just an example of something we could do in the browser. And then the next thing that we did was we set up a terminal or a console in Linux. They're called pseudo terminals. In Plan 9, they're called consoles. Here, I call them terminals. We create a terminal, and this is all made up, by the way, but it was kind of a guide and sort of thinking, basically a way to design the system without having to build it and kind of think through it. So we could create a terminal, we attach it to the body that would create a xterm terminal on the web page. And if we look in that terminal, we can see we have a control file and a couple of other files, data in and out. And then if we were to write to the out file, hello world, then hello world would show up in the terminal that's in the browser. Reset it. And then we'd create a virtual machine, because there is this VM device up here, and that would use v86, a WebAssembly based virtual, an emulator, x86 emulator, and create an instance of that, which would kind of initialize the virtual machine. And then we would use binding, and binding was a big feature of Plan 9, is sort of like symlinking, but a little more deeper and powerful than Linux symlinks. But we'd symlink the TTY, so the terminal input for the VM, to the terminal data line. It's almost, because these files represent read-write basic stream of bytes, you can think of it as like a data line. So this would wire up the console of the VM to our terminal that was on our page. And then if we started the VM, then suddenly a virtual machine would boot up in our on our web page. And maybe that's all very abstract, like I'm not showing it here, but it was in the last stream. Now our goal is to try and make this real, and I think we're pretty close. So that's kind of our initial goal here. And the last thing that we were working on was this DOM device, which actually was not really demonstrated in this prototype, but was kind of a way to start getting used to integrating with the browser environment. And I'm not sure if I did this by the last stream, but I did implement a a way to interact with the browser file system APIs. A lot of people don't know about this, but there's sort of a standard API for working with file systems in the browser, somewhat experimental. The original use case was you could call show directory picker, and that would give you kind of a file open dialog, and you could pick a directory on your computer. And then that would allow the web page to have access to that directory, which is kind of crazy because that allows you to make applications that run in the web that actually save data to your computer. I haven't seen a lot of people fully take advantage of this. There's also another way to use this pretty much same API to deal with data that's stored in the browser across sessions, called the origin private file system. Origin meaning the domain. So it's very much like local storage or some of these other browser storage mechanisms, except it gives you a file system like API. You can store things at paths and read files and write files. And then those files would persist. And we use that for this Aptron proof of concept that Rohit helped out with. And I always forget, for some reason, my browser is in a state where it never works. But if anybody were to go to aptron.dev, it will probably load a file system here in a shell and show a README. Anyway, obviously, if the browser can give us a file storage API that's like a file system, that would be really great to expose to Wanix when it's in the browser. So that's what OPFS is Origin Private File System. And it's the same API that's used when you do a file picker. This is a package. I guess it's FSA, short for File System Access API. But it basically implements a file system, which again just means we just have to implement open and or open context, and anything else that we want to support, like make directory, etc. And basically wrap the API that Wanix uses, which is very similar to the more POSIX-oriented Linux, Unix API. And all it's doing is wrapping calls to this browser one. It's actually very different. For example, once we get a file, get a promise, of course, we're doing promises because we're in the browser. We need a file system file handle, and a file handle has kind property, which is whether it's a file or a directory, has a name. You can, once you have a file, you can call get file, which is this kind of feels like a slightly contrived. It's not, I wouldn't say the best ergonomically designed API, but I don't know. It's what we got. So once you have a file, calling get file returns a file object, which is very similar to a blob, which is a sort of a data type in the browser that represents, a raw file data. And I think it also has a MIME type associated with it. So file extends that. And that gives you an API where you can directly access the bytes. You can slice into the bytes. You can get a readable stream, which is the browser's API for streaming. The browser API is way more complicated than it needs to be. that only gives you read access. If you want writable access, you would then say create writable, and then you get a writable stream, and writable streams work. They look a little bit closer to Unix stuff. Write to them, close the file. And then there's this third API, which is a sync access, because so far all of these APIs return promises, whereas sync access gives you an API that is synchronous and actually looks a little bit closer to the POSIX file system API. We call close, flush, read, write, even truncate. And these don't return promises. And these are only available in web workers, because web workers are essentially threads that run in the background. So it's okay if they block. And so this gives you kind of a high performant API for working with file systems. Anyway, all of this stuff has been wrapped up and in this file system that we've implemented for Wanix. We say open. We do some weird stuff because we don't actually know if something is a file or a directory, so we just kind of have to call and see what happens. If it's a file, then it'll return fine. We'll return a file. And if it returns an error, then we'll assume it's a directory. Sort of opening a full file path requires sort of calling in a loop, get directory handle several times, because there's no sort of equivalent of open where you can just give it a path. So in a way, this gives us an API that is, much more familiar for people that have worked with the file system, but it's sort of wrapping that more complicated browser API. And we even try, if you do have access to the synchronous API, it'll try and use that. So otherwise, you can see that, a file close, all stat, basically just wrapping all that stuff. Once we have that, we can use that same sort of wrapper for what I call like a picker FS, which is show a dialog to pick a directory, or access the origin private file system. So let me show that really quick. And then I can also show the DOM device, which kind of evolved a little bit since last stream. For this. And so as we're working on this, we're kind of working with a blank page. Wanix. That's our Wanix object. And I don't know if we had these before, but I made some little helpers here. So I can just say like list root. It'll give us the root directory. So DOM, let's look inside DOM. There's a body directory. This was some of the last stuff we worked on. So we can do a read. Let's read DOM body HTML. And that's the HTML of the body tag. So we're able to sort of introspect the body from here. We can even look at the attributes, although I'm pretty sure body doesn't have any attributes. And if there is text, etc. Let's see, something else that we had in the DOM though. There was new. Let us make currently just create a new div or a new iframe. And this works just like all the other sort of resources that we've made. So we can first do a read DOM new iframe to make an iframe. That gives us a resource ID of 1, which we can now see is a directory under DOM. And I think, and so this has not been attached to the body. It's sort of just like using JavaScript and saying create element. Just have a pointer to an element that isn't attached to anything. So from here I think we can write some attributes. If we did DOM1 attrs, let's see, basically all remember if we need to do quotes or anything. Let's do and of course we can't see that it's done anything because we need to now attach it to the body, which I'm pretty sure this is one of the things that the system doesn't do well, is when you have control nodes, you don't know what commands you can send to it. So that's something we might do where maybe if you read or pass help to it, it'll output what you can have. Let's look our source for. All right, basically supports one pen child and then the DOM ID, in this case the numeric ID. Matching it right to DOM body CTL pen child, very similar to the JavaScript method that you would call one. Okay, so it looks like it worked. We it attached the iframe to the body so we can actually see it now, but it looks like the way I parse attributes actually want quotes because it's got quotes in there. I think though we could just set this again, maybe without quotes, and it loaded my blog here in the iframe. And then another cool thing that we can do with the DOM device is there's a style file here, which if we write to that, we could just write CSS. We could say body, background, red. And so that behind the scenes is just creating a style tag and giving it the text that we did, and it appends it to the body, and so that applies that style. You can see how we're using this file system API as sort of a, at least in the context of what you can do with Wanix, as a sort of universal API. And then because we're on a web page, we can actually interact with the DOM using that API. And the idea is if we had a shell, we could be doing this with, cat and echo, or using whatever tools that normally work with the file system, which is most tools. We could open up Vim. We could say open DOM style with Vim and then write body background red and save and quit, and then that would make background red. So that's the DOM. Does that make sense so far? That's kind of, I think, what we were working on last. There were some other bugs that we ran into, I remember now, that were specific to we were getting this finalizer ref not implemented. Apparently TinyGo's WASM support doesn't support finalizers, which is kind of a special, or kind of a advanced feature of Go, and basically just commented it out because I can't really do anything about it. Maybe at some point TinyGo will support finalizers. That would make sense. But that's kind of the trade-off of using TinyGo. It's not fully implementing all of Go yet.
But is it worth like submitting a feature request to them or something?
That's a good question. I mean, we can actually check to see if there's any. I didn't look. Looks like there is an issue here. So, this has been open for a few years.
Well, that's too bad.
It looks like some people are maybe close to a solution. But it is basically a mechanism for usually cleaning up. It's something that's triggered when the Go garbage collector tries to clean up the memory. So effectively, by not implementing it, there's a memory leak. We're doing all kinds of, this is sort of advanced experimental stuff, and so I can live with a memory leak. It's not getting in the way of us getting stuff done, but we just have to know that there is a potential memory leak, but at least it's being tracked.
On principle, I don't like it.
Yeah, right. That's a good engineering mindset. I'm more of a pragmatic idealist where, maybe it's not that big of a memory leak. I mean, it's probably for strings and stuff. So it really depends on how you're using it. And, at some point it's a big deal. But the fact that there's an issue for it and it looks like they're close to it, it's something that we don't really have to worry about. So in the meantime, I just commented out this console error thing.
Gotcha.
And if it is a big deal, we can always go and use quote unquote Big Go, the official Go compiler. That'll just produce much larger binaries. So that's the trade-off that we're kind of dealing with using TinyGo. And actually, one of the big motivators for this rewrite is TinyGo getting support for some reflection stuff that was required by Duplex, which is what we use for pretty much any communication in our little ecosystem. For example, it's how we communicate over a message channel to talk to the WASM code from the browser context is actually done over Duplex. And so Duplex used a little bit of reflection. I don't remember what, but for the longest time, TinyGo didn't implement all of Go's reflection. They still don't, but they implement enough now that we can use Duplex. And so that kind of opens up all of this. Before the Wanix that is here, and actually someone recently submitted a bug report because these demos, the files that we had, partly because we were just like bundling everything into the binaries, like a 60 megabyte binary. Whereas now our sort of using TinyGo, we can actually get much smaller binary.
How small, like a tenth of the size or smaller?
So if we were to compress, and this doesn't do everything that the old Wanix was doing, but this is sort of everything, the kind of core stuff that we're doing so far, which, has Duplex, and we've got these file system things and everything. It is now 2.5 megabytes, which actually was kind of a little bit bigger. At some point it was 1 megabyte, so I'm wondering what dependencies were added that made it bigger. But once compressed, it's actually like 400 kilobytes.
Pretty good.
So that's a huge improvement over previously, where previously we had a loading screen and everything. And this is actually small enough that you could use this as, like, maybe you don't want all these DOM devices and you just want a virtual programmable file system in the browser. There are plenty of use cases for that. You'd use the Wanix kernel just for that. And it would be tiny enough that you could do that without being like, oh, Wanix does all this other stuff too. So OPFS, I don't remember if I got this just to show it. If we list file systems, new pickerfs is kind of what I call it. There isn't really a name for, oh, I can open files in the browser. It's just like basically show open file picker or show directory picker. Like as a feature of the browser, I guess it's just, you know, the name of the function that you can call. I think in somewhere is referred to as the file system API. So anyway, just made up a name, pickerfs. We can make a new one. We'll read fsys new pickerfs. File system here that we first have to mount. So we will write to its control file. Pretty sure just, and then it actually calls show pickerfs. I guess this is my go path. Directories here, we'll pick this. And then now there's a mount directory and we can see those files. I don't know that write support is working yet, but now we could theoretically create systems that can work with files on your host computer. You just have to create that file system device.
Pretty cool.
Okay, so we're pretty close to the paper prototype. You know, we have all this. This idea of a terminal device, I'm wondering if that could just be collapsed into a special DOM resource type. In fact, so usually what this means, there's this idea of an abstract terminal or console, which is basically what a pseudo terminal is in Linux. It's really just plumbing. It says you start a program in a terminal. A program normally has standard in, standard out, standard error. But then a terminal is just input and output. A terminal is what any terminal you're using is sort of going through this kernel resource that is doing a number of things, like supporting, special characters, like it can make the terminal beep. Like there's a whole sort of API for terminals. But for the most part, it's just wrapping, like, here's the output of this program that I ran, and it shows in the output of the terminal. And then when I type, That's the input of the terminal, and then it sends that to standard in. So it's kind of just a plumbing mechanism. And there are different modes and stuff like this. It gets it to really kind of archaic, complex Linux, old Unix stuff. Plan 9 sort of redesigned it and simplified it, but I'm wondering if we could simplify it even further. I typically use xterm.js as a browser-based terminal emulator. So this is a thing that you would attach to one side of a pseudo terminal. This is the library that VS Code uses. So this is xterm.js. This is pretty much the standard for browser-based terminals. And it's pretty simple. You instantiate a terminal, you attach it to some DOM element, terminal div, they open and then attached. And then you have this object you can read and write to like a terminal. And all this does is, show stuff in the terminal. Terminals also have, I guess, some other things that are important, like the ability to resize. So when you resize a terminal, it actually sends a signal to the program that it can re-render with the new dimensions of the terminal. That's something a little extra than just like reading and writing bytes. But I'm wondering if this has been packaged up as a web component. Yes. Doesn't directly provide a web component, but you can wrap it in one. So, web components. Are you guys familiar with web components? Maybe Rohit not as much because web tech thing. Have you heard of web components, Rohit?
I don't think so.
Okay, that's
Is it?
basic. I mean,
Yeah.
and it's not even a totally commonly adopted thing yet, for various reasons that I won't get into. But basically, it's most of the time people use frameworks like React. I use Mithril, a lot of alternatives to create almost like custom HTML tags. But you need that framework for that to work. Web components was this idea to make that general idea more native to the browser environment, so you don't need a framework. And so it effectively lets you create custom tags that you can use on your page. So it's basically a very native version of, a dynamic web thing. And it's pretty much as simple as extending HTML element, which is a built-in type of the DOM. And then it looks like if you already have, xterm.js is already a library, so it's already doing most of the work. So it looks like creating this wrapper is not a whole lot of work. And then you say define xterm element. Here's my class that I created. So then you can say xterm element, and this will effectively do the same thing as this code. This code. Instead of creating a div that you attach it to, just create it and it will already. And so that's
kind of like.
Yeah, it's kind of, well, I'm trying to see, let's see, if we read this, it's going to create terminal. Bit add-on is basically something that will watch for changes in the browser to send that signal to the terminal, to send the signal to the program that it's been resized. The fit add-on is a very common with xterm.js. So it adds that, and it says open this, which means this element. So it's sort of attaching it to itself. Fit will then cause it to resize based on the size of this element on the page, depending how it's styled. And then it adds an event listener. So if you resize the page, it's going to call fit again to trigger a so for this, you still have to include the CSS for it. You still have to include, the scripts that would include xterm and this custom element code. But once you have that, it's now sort of like a native element. So for that reason, I'm almost thinking that we could create it as a custom DOM element type in our DOM where are the new? Oh, it's new. Okay, we created a system where we could register types, and here's where we register div and iframe. So in theory, if this was just another element, we could just add, xterm terminal or something like that. So I'm thinking of exposing xterm in that way, even if we don't set it up at using web components yet. At least in Wanix, it will be a custom type of element and create. And for now, it can just set it up behind the scenes using the traditional API. But that would get us to a point where we could create a terminal that's on the web page, which is kind of the last step before creating a VM or an emulator. And that's where we get into the fun part of being able to wire stuff up using bind. So in this example, a VM has a terminal, and then we can attach it to the terminal that we have on the page. So the only problem is, well, I guess this is, again, we're kind of in prototype. Take some shortcuts. This HTML page, for example, we can kind of already have xterm stuff included. Best way to do that. We could load from a CDN, but always run into problems with that when I try to work on things offline. There's a project. I guess it has its own term. So you write enough code, you can end up just try to search. we go. I'm just doing this to get these files. And putting it on the page looks like this. It looks correct. I guess we could, just to make sure, create a terminal. Works by hand. Separate. Works. Get element by ID. And serving. So we should. All these changes are going to hello from JS. So we have xterm source code loaded on the page. So now we can just add some stuff to Wanix that will effectively do this. So out. DOM implementation, and let's see, what do we want? So when we create these, it's the effectively, yeah, the result of create element. But in the case of xterm, we need to do something different because we can't just create the element. Once xterm is packaged up like a web component, it could be more consistent like the others, but I don't want to bother try doing this right now. So we'll just kind of special case it in here, I guess. So at this point, once we create an instance, that will be the equivalent of terminal new. And normally these other elements have to be attached to the body, but that's not exactly how this works. Instead, we call term open, give it an ID. So I'm trying to figure out when that will happen. I guess we could maybe special case that. And child, look it up and see that it's a particular. You'd see that it's xterm, and instead of calling a pen child, we'll do this. It's almost like, again, in theory, if it were a web component kind of thing, it would be exactly all of this, but I'm special case. I know that that works. Okay. So term if term, let's see, what is it going to do? That's not exactly what I would have done. Doesn't really what we're trying to do. But we want to call instance. I want to store that somewhere too. I guess. Just a JavaScript value. Doesn't matter. We'll just try storing. Global. So when you include xterm.js, it makes terminal the global. Be able to just get that and create a new instance of it. I guess we do. And down here. This is our type string. That's xterm, so pretty close. I'll open and then give it ID. I guess actually we do need to create an element for it to attach to. So that's interesting. We still need to create an element. Let me think about it. Then we'd have to I guess it would we'd create a div or something, and then it would attach to body, and then I guess also call open. So it's really just extra steps. We still want to create an element because we need something to sort of open it in. So do this. Terminal new. Nice thing about JavaScript is you can just kind of like put stuff on things. So in order to keep this reference around, we can put it on our element. Create a and that term okay. So now when we create xterm, it's going to create a div, then it's going to create a terminal, and then put that terminal instance on our div object element because it's JavaScript and we can do that. That's stored here. Then we want to append child, and then after append child, we'll call open to will open and somehow need to pass, I guess, the element, which would just value. I think that's all we have to do. Later we'll figure out how to sort of bundle this so that you don't have to worry about including these resources, because they need to be included on the page. But if this works, then good place for.
I was just gonna ask.
So we're including the files, but we're not creating terminals. So there's blank page. I didn't build. Builds WASM. Xterm. Term 1. And then in theory, just write to DOM L 1. Oh, there's the terminal. That went pretty smooth. Yeah, and it feels a little weird that kind of doing some special case stuff, but at some point we'll figure out how to package up xterm as a web component, and then in theory we could take all this custom code out because it would just be, you know, custom element here, and then we just have to figure out how to bundle all that stuff with Wanix, or maybe have it detect, you know, if xterm.js is loaded, then this becomes available. Otherwise, not. But cool. All right, so that's xterm. Let's take a break. How long?
Woo. I don't know, 5 minutes.
Okay. Back in
12:06.
Okay.
I'm back.
So you are.
Hello.
We're all back. Okay. Get back into it. So it turns out I forgot. We don't just want to create an xterm, but we want to expose its being able to read and write data to it. Well. So, again, we'll just kind of hard code a new thing. Right now, all elements that you create with the DOM device have a little subfile system like this. There's a control, file, type, attributes. You can see how we're using a version of this field file that we made a while back, where we can define what we read from the file with a getter function, and then also what we do with data if we write to it. And you can see how we're just calling DOM here to set attribute. This is where figure out how to deal with the quotes. But so my plan, just as a short-term way to expose the read and write of the terminal, is I guess to check to see if it's an xterm. Ooh, let's see if AI is gonna get this right. Almost. So I got this idea that I have a data file for this resource, but unfortunately, it's going to be more complicated than that. It's also a stream, so it's not just getting data or setting data. I guess if we write to it, that's pretty straightforward, because we're just passing that through. And if we read from it, though, that would be more of a stream. Let's, I guess, use this as a start with. For now, we're not gonna do anything when we read. But writing to the terminal is very all right. So this is set up so whatever we write to the file basically shows up here, and we can do whatever we want with it. It doesn't happen until the file is closed, but typically you would write to it and close the file. At some point, it's going to be a stream, so this won't really work out. But for now, like it kind of figured it out. We store a reference to the terminal object on our element. We can just get that off of value for this element. I'll write on it. So in theory, we can now create a terminal and it'll have a data file, and we can write to that data file and it'll show up in the terminal. It's at least a step in the right direction. Do the same thing for xterm child. Look at DOM. One for it. We see there's a data file. Write to that. Goes up in the terminal. Well, that was easy. The problem is it is a stream, and the way, I guess we can back to that when we get the VM.
You don't want to deal with it now? I'm just curious.
Good, but I don't actually have any helpers that would actually let us test using it as a stream, I don't think. But we'll use it as a stream, or the VM will use it as a stream. So if we get the VM stuff set up, then we can test this. And
Gotcha.
although I guess in the paper prototype, all basically just baking open. Our xterm term ref is a reference to the terminal. You can see here in the prototype I had sort of like separate files. There's an out file. It's sort of like what the terminal sees. So writing to that would display something in the terminal. That's what this is. This is kind of what we just done. And then when we set up a VM in that prototype, it would automatically wire things up in a way that I wanted to be able to do by hand using bind, so that it's a little bit more of a more powerful mechanism. Instead of the VM sort of being hard-coded to write data to the terminal, like how does it even know that there's a terminal set up? Is that you would set up a VM and then call bind, and then through that binding, it would know that when the VM gets the VM has a terminal set up on its serial port. So we can basically set up listeners for when bytes come out of the serial port, in which case we would just write them directly into the terminal. And when the terminal has data, basically when we type stuff, it has a callback on data. And in this case, we would just send bytes over the serial port. So to do it more decoupled, we kind of have to set up more mechanisms I haven't totally thought about yet. So for now, let's, I guess, start with this, the VM stuff. And kind of like xterm, we're going to kind of just take a shortcut, because the actual device I want to do for VMs is almost recreating Docker. And this actually leads into env86 and how env86 might be rewritten to use Wanix to do some of the stuff that it does. But for now, just to kind of get this example working that kind of looks like this prototype, we can take some shortcuts. For example, configuring the VM, we'll just create a predefined VM. In fact, I guess, just to see what happens. New v86. So it's a lot of work to set up a VM or v86. It looks like this if you do. Boots up a little Linux kernel and loads into Alpine and all this cool stuff. But instead of doing that immediately here, we could wrap this up in a function, and then when we create the resource on the file system, it'll just call that function. Later we'll kind of expand it out. So I'll start on the VM as well. No, looks like it just starts. Oh, because auto start. Okay. So, I don't know, we'll call this make. So now there's a global make VM, which we can use. This up. All right, let's create our new device. And for now, this is, even though I want these VMs and stuff to run in the native version of Wanix, it is kind of assuming WebAssembly and stuff. So it's under the VM thing. We can use the DOM device as a starting point. Delete a bunch of stuff. Let's see, there aren't types. Just VM that you can create. So actually, instead of new being a directory, new will just be a font. Is this how we would do that? So this is a file system. If name is dot, which means new. I guess we'd error. No. Comma? I don't know. Something what am I missing? Turn. Nil. Close this. Oh. In the case where we try and open anything else. Turn. Exist. And we don't have types, so we're just gonna we don't have to allocate anything really, because we're going to we should allocate. Right now this auto starts when you set this up, but maybe we should have start be something you call in the control file, which is kind of how I modeled it. Allocate a VM, and then you have time to set it up and wire things up, and then you can call start. So we will allocate it by calling VM, and what that returns is a reference to it, and we store that in the value. Element, though, we might rename. Okay, and we don't have any of the body. I guess we can call this no factory. Know if we need a reference back to this device. That. All right, so VM basically has one file new, which will allocate a VM by calling make VM, stored in the resources here. Of course, we have all this code that will show the resources once it's created, so there'd be a one directory that would point to the VM that we created, which it would have then this file system. And I don't think we need this DOM stuff. I'm trying to remember what else. A VM would. Oh, file system. What image was used? All this stuff gets into kind of doing the banded version of this. It's a lot more work. So for now, we'll just have a control file that we can call and start to. And takes one thing. Our value, which is basically the return of this, which should have, I think, a start method. This is all. This also uses the same x86 stuff. And so somewhere in here we started. Start. Run. VM start. What does this do? Maybe env86 is set up to just auto start. Go look at source. Oh, it might be run that we want to call. The v86 API is not super documented and not super consistent, but it looks like we want to call run. So we call it start. I think it should be run, start, but we want to call run. Okay, so if make VM does most of the setup work, at some point we'll have to make that part of this, but we'll do that later. And then once it's created, once it's allocated, we can send to its control file start, which would call run, which would start up. And then in our WASM version of the kernel, we can add, I guess, this. Do same here. This mounts it as a hidden file system, and then I guess it depends on specific stuff. Where bind it now as okay. Let's see if we get a VM to boot up via the Wanix file system. So instead of it booting automatically, we turned it into a function. So that is by VM. Need new. Okay. So I guess that does at least set up whatever, some DOM stuff. Not booting it yet though. Whoops, I created two. We'll ignore the other one. And there's a control file, so we can write VM1 control start boots.
Yay.
So we took some shortcuts, but effectively it kind of good enough, equivalent to what was planned in the. And actually, just as a little extra bonus, one of the things that I've been working on off stream is bridging the v86 file system to the Wanix file system. It doesn't totally work yet, but go to test. Whoa, DOM, FSys, rock VM. We just added that. This is live stuff. What's in DOM? Whoa. So now you're starting to see, like, in theory, we could actually start doing stuff like echo, body, background, red, right? And then write that to DOM style. This does not work because reading and writing data has not been implemented in this bridge, but you can at least, navigate.
Imagine it.
Yeah. I mean, we even have, you can see that we made two VMs. They're both showing up there. So this is actually using the Wanix file system. We just can't actually read or write data other than the seeing navigating the file stuff. So that's a little preview of where we're going with this. So the idea is, previously Wanix had a shell, and that's, we wrote a custom shell, and we had to re-implement a lot of the stuff you'd normally have, like copy, at, echo, cd, all that stuff. You just kind of like take for granted. We had to implement, and it was custom to Wanix. This new version with this new architecture and focusing on this VM, the way, all this sort of stuff that I'm showing in this prototype, this isn't how you would normally use Wanix. This is just sort of like how a preview of how Wanix works and how it would bootstrap itself, in that, at some point you would set up Wanix and it would automatically, depending on what we want the experience to be, it could basically, instead of booting into a shell, it would boot up, a custom shell. It would just boot up a little VM that is a totally minimal Linux kernel and system, and you would primarily use it to interact with the Wanix file system. So then you can start. You wouldn't actually be doing all this stuff in JavaScript or in this console. You would actually be doing it in this shell, and you'd actually have, and from there you could create other VMs and run other, Linux programs, and they could all have access to all the weird stuff that we put in this file system, including, for example, I wish it worked, but we could do what was it? Pickerfs. So read Pickerfs, and then go that, and so in theory you would be able to do that here. I think part of the problem with this bridge is it doesn't update. So there's a 1 here, but it's not here. But if it did have, you'd see a 1, and then we could go into that mount, and you would have access to your host system's directory, whatever it was, and we could do stuff from, in this kind of Linux environment. So Wanix isn't really an operating system. It's almost more like a hypervisor, which is an operating system that is designed for running virtual machines. It's like what, AWS runs, and all these cloud providers. The actual computers that they run, they're running a special operating system called a hypervisor that's just made to boot up virtual machines. And then as users, you use those virtual machines. So very similar idea here. But it would also then, we'd kind of work in ways to run not just, so if you have this emulator, the v86, x86 emulator, so we could actually run x86 programs in the browser, in this environment or wherever, and they'd have access to our file system stuff, shenanigans. So you'd be able to run cool, whatever, most programs that you could run in Linux, you would be able to run in Wanix, but you'd also be able to run WebAssembly native stuff. So at some point, we could actually take the shell that was made for old Wanix and run it in new Wanix as well. It just wouldn't be a requirement, I guess. We would, by default, we could just ship with a minimal Linux shell. Okay, what? Got this out of. Okay, how do we wire these up? So the thing is, this is not our terminal. This is when you set up v86, you give it its own element. It kind of writes to it like xterm, and actually when it boots up its graphics driver, it actually attaches to a canvas, which is basically like a bitmap display. You'll notice I can't select stuff here because this isn't like a normal terminal or text element. This is a big canvas element that's more or less rendering what a screen would output, like a video card. And so what we want is that terminal that we can create to be how we interact with this VM. So the way we do that is this VM has an interface to its serial port, and we want to attach that serial port to that data line of the terminal that we made. And so that's where we get into stuff I haven't figured out how we will do it. But let me make sure that we can still create a terminal. I think it would don't actually use this, and it would be appended to the body, so it would show up after. So if we create a DOM new xterm, then attach it. Child 1. Okay, so it creates it down there. So this is what we want to interact, and we can just not show this. But work. So we're going to want to do something like this, except we can't directly couple them. We want to almost create a pipe. Data, set this up. The goal is to somehow the VM has no idea that we have a terminal, but the VM can be set up to read and write from a file that we can set up under its little file system. So list VM1. Right now there's a control file. The idea is if we were to create a file in here called TTY0 for teletype terminal 0, that it would use that to read and write the output of its serial data and read it to send data in. And then the idea is that if we were to use bind, we haven't used in a while, but basically it creates an alias, then we could take the this data here, DOM1 data, and we bind it to VM1 TTY0, then that would cause the data that's coming out of the serial port to be basically joined with this data file. And this is sort of, I don't know if that might be too abstract and it'll be easier to kind of see, but that is sort of the basis of some of the power and control that you can have with this system, is that you're effectively able to sort of like wire things up, kind of like take the input of this system and pipe it into the output of this one or whatever. And you should be able to do that with bind. And so again, we're not adding any new capabilities. This idea of kind of creating a binding will let us do that kind of like wiring things up. And so this is just one example of that. You can imagine creating devices that are actually like, I was talking to Stevie about doing audio synth stuff. It's almost like modular synths, where you create a device and it represents a sort of a modular synth thing that has, a bunch of inputs and outputs, and you want to wire those up to another device, the input of that device. So that's kind of an interesting metaphor to think, where you could instantiate these audio devices in a system like Wanix, and then use bind to basically wire them up like you would in modular synths. And so that's kind of the metaphor.
Sounds like a fun demo to make.
Right, exactly. In fact, that's a whole potential project that could be done on top of Wanix, is a modular synth system. But this binding, this is kind of the first, this is the first step, the first instance of getting that kind of wiring things up to work. That's why this is kind of important, but I've only thought about it abstractly. I'm trying to work out how this will work. We want, when we create a VM, before it's started, or potentially when we start it, if it's able to look at its file system to see if there is a pty0 file. So maybe that's a place to start. Let's try binding a file. I don't even know if we can. I think we can bind a file to a device that we made that's normally, because this is not a directory that we can just write files to. If we had the ability to like echo into a file, it wouldn't let us, because this file system is defined by this, which pretty much doesn't let you do anything but open up a file called control. But because we're using namespaces, we should be able to do that. So namespaces basically give us like the ability to overlay, and when we do bindings, they show up to the namespace viewer. Well, let's see. If we had maybe body style. Let's try and bind that in. And I forget how to do bindings. I think it's through process. Bind. Okay, yeah. So a while ago, we created this proc file system device. Right now, it doesn't really let us create any processes. Obviously, that's kind of a key part of any operating system, is the abstraction of processes. And eventually, you'll be able to create processes, WASI processes, or native processes, or processes that run in the VM. Right now, we just have an empty or a namespace process where it doesn't actually run anything. The whole point of it is just to create an instance of a namespace. And everything that we're doing with this file system is actually through that namespace, which we can see, we create a sort of an initial namespace process, and all the operations we're doing are actually through that namespace. So that's why there's a proc here called 1, and we can actually look at the namespace. And if we look at it, it looks like our root directory because that's literally what it is. So this whole time, we're not really directly working with the file systems. We're working with it through the namespace that we set up. That's what these bindings are actually doing. Because normally these built-in devices that we've been making normally are hidden. They have a prefix of pound, and so they don't show up. But when we create a kernel, it actually creates a new namespace, which we can then bind stuff into. And so we bind the hidden devices to non-hidden ones, and that's what we see here. The whole point of this is that this becomes a way of exposing capabilities to processes. So if I were to create a process that runs some WebAssembly or, as a Linux shell or whatever, that I could actually, before it starts, I could actually remove these bindings. And so you could say, oh, it doesn't have access to the DOM. It doesn't have access to VMs. It can't create new file systems or bind new stuff in. And so that gives that process a unique view of the Wanix file system and the capabilities that are exposed with it. That makes sense? I'm sorry, this is all very abstract, but it'll come together. You'll see. It'll make sense. But the point is that we can make bindings by operating on this process. So using this process as control file, we can bind. Oh man, how does this work? Source to. So, for example, we could use this to create another, proc. We'll call it. I'm remembering what is which. Source to proc 2. Now our root has a proc 2, but it is literally just proc. It's just another way to get to it, I guess. So we can use this binding, and this only works for our process. If there was another process, they wouldn't necessarily see proc 2. So this is the whole, just one of those kind of architectural design things that we're pulling from Plan 9, and they've sort of already proved it out. And so it's not like I'm like, oh, this is in theory. They figured this out decades ago. But nobody's really taken advantage of it since it kind of was a never used outside of research. So yeah, let's kind of do the same thing. We'll take proc, but instead of putting it at proc 2, we'll put it under VM 1. and we'll pretend we're creating a Y thing. Okay. So the fact that it's a directory, whatever. But the idea is that we would be able to do this with, oh, we don't have unbind. But we have a DOM one. We've got that data line there. Is that we could do DOM1 data, create this binding. And so now this tty1 is the data file for that terminal. And so what we want now is to basically from our VM file system is read this file or be able to open this file and then use that as a way to feed material input and output. But we're pretty much at the end, so that gives me till next time to figure out how to do that. But that actually gets to what these contexts are about, because we need to, from this file system implementation, is somehow access files that are only visible through the namespace that we're using it from. Trying to sample it from. So the fact that we can actually wait a minute, where is self? Uh-oh. There's something I have to figure out, but if something isn't calling with context, then we lose context, and then we PID is how we can get to the namespace. But it's not working. We should see self under here. It would return 1, but something's not. We'll have to figure that out, but almost there. We can almost wire things up, but meantime, we did get a start of a VM device, and we did actually expose the data. So this will hopefully be done by the next stream, which is Monday, and we have lots more to do after that. Fun. Okay.
Yeah, good progress.
Yeah. Any comments, Rohit? Are you totally lost? I'm sure this last part is very...
Yeah, I'm not totally lost. I mean, I understand what's happening. But it was like a lot trying to... What? Can I have like one question?
Yeah.
So if we have the terminal up on the on the view now,
Mm-hmm.
why are we trying to do still some stuff in the console, like listing and binding?
Why are we using this?
Yeah, I mean, can't we just use a terminal for everything?
We can, but what we're trying to do, well, yes. Problem is, I haven't implemented the ability to read or write any of these files that we can see in here. So it's not totally finished, but yes, once that's done, we don't have to use this anymore. We can actually do it all inside the VM. But of course, we didn't have this VM really set up until now. But even then, we don't have the ability to actually read or write from these yet because it's just not fully implemented. I think it was just the other day that I got this playing back. But once it is, we won't have to do stuff over here.
Well, I was confused if it's using the same Wanix system. Why do we have to keep moving around?
Right. But and this isn't a totally, I mean, this will be good enough. There's ideally these VMs are configurable almost like Docker. So right now we created this VM and just kind of came up and it's like, oh, well, it's has Alpine in this version of Linux and all that, but all that will eventually be configurable through the file system as well, obviously. And then, so you can create different Linux environments that would let you interact with Wanix. But we're still not there yet because we can't read and write data from this yet. And ultimately we want to interact with it through the terminal that we created here. Even though we can interact with it here, but this is not a proper terminal. This is just a canvas. It's just a rendered image. So this terminal is based on xterm, and we can't actually use this to interact with it until we get this kind of wiring up mechanism. So that is what we'll have next time. Anything else? I guess it's the end of the month, so I mean, you're free to join these streams in the future if you want as a viewer.
I'll join some few watch how it where it goes.
Yeah, because it's like now that you've gotten this far, how are you gonna know how it's gonna end?
Yeah.
But it's been good to have you with us, and I hope you got something out of it.
Yeah.
No, thank you for having me. Thank you for letting me shadow you and see how everything is done.
And I know it's possibly not relevant to anything, but maybe Wanix will end up being useful or interesting at some point, and you can say I was there.
Yeah, it will be. It's interesting.
Cool. Well, I guess that's it. Bye, everybody.
Bye. Thank you.
Bye-bye.